In this section, we're interested in knowing whether or not our paired or matched data has a linear correlation. Now, a set of data can have a positive linear correlation or a negative linear correlation, or it could have no linear correlation. So how do we determine whether or not a data set has a linear correlation? And then also, how do we measure the strength? So an important vocabulary word for this section is the word correlation coefficient, which is sometimes called an R value. We use the notation R to indicate this value. It is a numerical measurement, and the correlation coefficient, it measures the strength of the linear correlation for your data set. So we typically measure the R value as a number that is between -1 and +1. So it can be any number including -1, it can be +1, and any number in between. The closer and closer your R value is to -1, the more, and I'll use in quotations here, perfectly linear your data is going to appear in a scatter plot, but it'll just have a negative relationship. And then if your correlation coefficient is +1, then you will have a perfectly linear relationship or correlation, but it'll have that positive trend. And then as your correlation coefficient moves away from -1 and closer to 0, you're going to see the scatter plot is going to look more scattered. And the same thing on the other side. As your correlation coefficient moves away from +1 and closer to 0, you'll see that the data has a weaker and weaker linear correlation. So if your correlation coefficient is 0, then that means that there's definitely no linear correlation. The scatter plot is going to appear really scattered. So real quickly here, I have 3 examples of 3 different paired or matched data, and they're all positive. They all have a positive trend, but I just want to show you the difference between a data set that has a correlation coefficient of +1. So here, let me redraw that line here. If I were to try to fit my data with a regression line, or what we call a line of best fit, hopefully you can see that all the data points fit on that line perfectly, and so the correlation coefficient is 1, and so that means that there is a very strong linear correlation between heights in inches and height in centimeters. In the next example, you can see that the data still has that positive linear trend, that pattern, but it's a little bit more scattered. So if I were to try to fit all those points on a line, they're not going to all fit on that line perfectly, but they're all pretty close to that line. So we can see here the correlation coefficient is 0.98. So it's not 1, but it's still pretty close to 1. And then if we take a look at again, so in example B, we would say that there is a pretty strong linear correlation between men's life expectancy and women's life expectancy. When we take a look at the last example, notice that the data still has that positive linear trend, but it's a little bit more scattered. And so the strength of that linear correlation between height in inches and weight in pounds, there's still a linear correlation, but it's not that strong. So here the correlation coefficient reflects the strength of that linear correlation, and you can see that it moved to 0.72. So these R values, right, as they move away from +1 and get closer and closer to 0, we see that the strength gets weaker and weaker. But what we have to ask ourselves is, at what point do we say that a correlation coefficient of, X value means that the data does not have a strong linear correlation. Therefore, we should not say that there is a linear correlation between the two variables. So where is the cutoff? There has to be a cutoff because it can't be subjective, right? You may look at this and say that that is a weak linear correlation, but I may look at it and say, I think that it's a strong linear correlation. So there has to be a way for us to ask ourselves, right? If you have a correlation coefficient of, let's say, for example, 0.72, is that still strong enough, right? Or does it have to be a number higher than that? So there has to be cutoff lines, and how we cut off those cutoff lines is what we called critical values. So critical values give us a range of values where we say, okay, if our correlation coefficient falls within this range, then the data is still strong enough to say that there is a strong linear correlation. And then if the correlation coefficient does not fall within that range defined by the critical values, then we say that the relationship is weak and therefore there is not a linear correlation between the two variables. So how do we calculate these critical values? Well, in this section for now, you will be given, oops, Okay, you will be given these values. So you can either use table 2-11 or you can open up the table in StatCrunch, or excuse me, in MyLab Statistics. Again, so there are two ways to determine if the data is linear. For right now, I'm going to focus on this first method, the critical value method. But you'll see that it doesn't matter which method you use. If you use the critical value method or the p-value method, it will lead to the same conclusion, meaning it'll either tell you that there is a linear correlation between your two variables or there is not a linear correlation. So again, for now, don't worry about how I calculate these values. You'll learn how to do that in chapter 10. For now, these values will be given to you and you figure out the correct critical values for your data set depending on the sample size. So the critical values, for now, it depends on your sample size. So let's take a look at that next. Okay, so if you are using, if you're doing your homework to get the critical values or that table of critical values, there's going to be a little blue icon here. So you just click on that blue icon, it's going to open up this table. And again, you can find the critical values on this right-hand column here based on the sample size for your sample. Now, the critical values given in the table, you're only going to be given the positive values, but you're going to see that you're going to need the positive values and the negative values. Okay, so let's talk about an example. Let's suppose that you have 5 data values in your data set. So your sample size is 5, okay? And then let's suppose that you are given, because you don't know how to do this yet, I'll show you in chapter 10, but let's say for those 5 matched or paired data, the correlation coefficient for your sample is, let's say that it is 0.591, okay? So now we want to ask ourselves, right, for a scatter plot with 5 data values in it and a correlation coefficient of 0.591, right, is this a strong linear correlation between our two variables? So now if we're using the critical value method, we're going to go to the table, and on the table you'll see here, so let me erase this, that if you go down to the sample size of 5, the critical value that corresponds with that is 0.878. So I always tell my students to draw yourself a quick number line from -1 to +1 with 0 in the center, and then mark your critical value. So here, our critical values, I'll write it down here. So our critical values from the table is going to give you the positive critical value. And then you just need to record the negative critical value. So it's just the same number, but negative. Right, so it's the same distance from 0. And then mark it, and I'll mark it in red on your number line. So maybe somewhere right here. Okay, so that's 0.878 and -0.878. So what the critical value does is it defines what we call critical regions. So the 2 red shaded regions that I've just shaded there, these are called your critical regions. Okay, if you're using the critical value method to determine whether or not your data has a linear correlation or not, okay, the rule that you use is this. If your correlation coefficient for your sample, so here the correlation coefficient for our sample is 0.598. If it falls in the critical region, then we say that our data has a linear correlation. But if it does not fall in the critical region, so if it falls anywhere in the blue region, which is not the red region, then we say that there is not a linear correlation between the two variables because that correlation coefficient, so let's go ahead and mark that. So I tell students, okay, now mark the correlation coefficient from your sample. So here, right, that right there is my correlation coefficient for my sample. We can see that it does not fall in the critical region. It falls in that blue region. So here we would say that there is no linear correlation, okay, between the two variables, right? And you can kind of use your own gut instinct for this because 0.591 is pretty close to 0. It's much closer to 0 than it is to +1, right? So here, this means that the linear relationship is weak, and so it's so weak that we say that there's no linear correlation. Now, let me use green here, and let's suppose, so let me suppose a different example. Suppose from your sample of, let's say, 5 numbers, okay? So you have a data set with 5 values in it, but let's suppose this time your correlation coefficient is 0.89, okay? So if the correlation coefficient is now no longer 0.591, but is now 0.89, right, is the data considered linear? Well, you draw your number line again, and then from the table, the critical value is still negative 0.878 and positive 0.878. So you mark it on the number line, so it's the same here. And it defines the critical region. But this time, when I plot 0.89, that's just a little bit above 0.878. So now our correlation coefficient of 0.89, we see that it does fall in that red shaded region, meaning it falls in the critical region, which is defined by our critical value. We can say that here there is so we say yes, linear correlation exists between our two variables. So that's how you use the critical value method for now to determine whether or not your matched or paired data has a linear correlation or not.